Back in 2016, a single paper came out and basically dropped the blueprint for the next era of large-scale AI. It was called TensorFlow, a system for large-scale machine learning. And the architecture it introduced? It was so powerful, it quickly became the industry standard. So today, we're going to deconstruct how its designers tackled the monumental challenge of building one system that could handle both bleeding-edge research and planet-scale production.
Okay, so here's our game plan. First, we'll set the scene and talk about the huge problems Google was facing at the time. Then, we're diving straight into their brilliant solution, the Dataflow Graph. After that, we'll see how they actually got this graph to run across these massive computer clusters. And then we'll get into why its flexibility was the real game changer. Finally, we'll look at the performance, the impact, and the questions that really set the stage for the next generation of AI systems.
All right, to really get why TensorFlow is such a big deal, you gotta picture the world back in 2015. The machine learning universe was kind of split into two. You had systems built for research, and you had totally separate systems for production. And they really didn't speak the same language. Trying to build a single, unified system that could do both, that was the holy grail, but it was also a massive headache.
So the authors of the paper, they laid out these 3 things that a new system absolutely had to have. First, it needed distributed execution. We're talking Google-scale data here. Second, it had to work on all kinds of hardware, your standard CPUs, powerful GPUs, and even custom chips like TPUs. And third, and this is the big one, flexibility. It had to be powerful enough for a researcher inventing a brand new model, but also robust enough for an engineer serving that model to 1 billion users, all in the same system.
And the tools they had back then, they just weren't cutting it. On the one hand, you had batch data flow systems like Spark. They treated data as this unchangeable thing, so trying to update a model's weights over and over was incredibly slow and clunky. Then, on the other hand, you had parameter service systems like Google's own DistBelief. They were great with changing state, which made them fast. But for researchers, they were a brick wall. If you wanted to try a new optimizer, you had to go and modify the core C++ code, which just killed the pace of innovation.
So the solution to this mess wasn't some awkward compromise. It was a single, powerful, and really elegant new idea that was designed to solve all of these problems at once, the Dataflow Graph. This idea became the core of the entire system.
Okay, let's build this up from the basics. The name TensorFlow really says it all. The tensor is the data. It's the what that flows through the system. And fundamentally, it's just a multidimensional array. A single number, a vector, a matrix, they're all just different shapes of tensors.
The flow part comes from operations. If tensors are the nouns, operations are the verbs. They're the nodes in our graph that do the actual work. Things like matrix multiplication, or adding 2 numbers, or reading data from a file. They take tensors in, do some math, and spit tensors out. This is the how.
And when you put it all together, you get the whole picture. The Dataflow Graph isn't just a sketch of your model, it's a complete blueprint for everything that's going to happen. Tensors flow along the edges, and the operations, or vertices, do the computing. Your entire algorithm, from loading data to updating weights, is all right there in this one structure.
And this right here, this is the absolute masterstroke. This is the key insight from the paper. See, unlike older data flow systems, TensorFlow introduced operations that could have mutable state. An operation like a variable, for example, could hold a model weight that gets updated in place again and again. This one simple idea meant TensorFlow got the incredible speed of a parameter server, but without giving up any of the flexibility of the Dataflow graph. It was literally the best of both worlds.
Okay, so we've got this beautiful abstract graph on paper, but how do you actually get that thing to run on, a huge cluster of real machines with real hardware?
Well, it's a really smart 4-step process. First, a placement algorithm decides which device gets which job. This operation goes to CPU 0, that one goes to GPU 1. Second, the system carves up the main graph into little subgraphs, one for each device. The third step is crucial. Anytime data needs to jump from, say, a CPU to a GPU, the system automatically sticks in these little send and recv nodes to handle the traffic. And finally, each device runs its own little subgraph and caches the results, which makes every following training step super fast.
Now this is where the whole Dataflow idea really starts to pay off, because everything is just an operation in the graph. All this complex stuff that used to be buried deep in the C++ core of a system was now something researchers could build and piece together themselves just using simple building blocks.
This was a total game changer. Things that used to take a systems engineer were now in the hands of the researcher.
You want to do automatic differentiation for backpropagation? No problem. It's not some magic thing hard-coded into the system, it's just a library that works on the graph. You want to invent a new optimizer, like Atom? That's just a matter of putting together basic math and variable ops. Even essential stuff like saving and restoring a model was handled by simple save and restore operations inside the graph itself. It made the whole system transparent.
Okay, get this. Imagine you've got a model with terabytes of parameters. It's way too big for any single machine. In the old systems, handling that was a massive engineering project. But in TensorFlow, it's just another graph puzzle to solve. You use an operation to partition your giant tensor, and another one to stitch the results back together. Splitting a huge model across a cluster wasn't a special feature anymore. It was just another thing a researcher could design themselves. That kind of power was unheard of.
But with all this amazing flexibility, there's always that one big question lurking in the background. What about performance? Did this general-purpose do-anything approach come with a huge speed penalty? Was there a trade-off for all this power?
And the answer from the paper was a huge no. They benchmarked the core system and found it could dispatch 2 million null operations per second. Now, that sounds abstract, but it's a test of the system's own internal speed, its overhead. And that number proved that the framework itself was incredibly lightweight and efficient, which meant all those precious hardware cycles were being spent on actual math, not on managing the system.
So the paper wraps up by basically saying, hey, it worked. TensorFlow was adopted everywhere and pretty much replaced the old parameter server model. But what's really impressive, and what makes this paper so important, is how clear-eyed it was about what wasn't working yet. The authors pointed out the need for better automatic optimization, and, most importantly, they identified the big limitation of a static graph. For newer fields like reinforcement learning, where the computation itself can change from step to step, having to define this giant, unchanging graph up front was becoming a real pain.
And that leads them to this final, really powerful question. This question basically laid out the entire roadmap for the next wave of ML frameworks, the ones that could handle dynamic computation. It anticipated the rise of define-by-run systems and set the research agenda for the entire field for years to come. It just goes to show the original TensorFlow paper didn't just give us a solution for its time, it perfectly defined the next big problem everyone would need to solve.